Okay, can you see my screen?
Yes, perfect.
Okay, great. Okay, so hello everyone, and I'd like to welcome everyone to my lecture. I'm Kazumasa Takeuchi from the University of Tokyo, and in this lecture, I'm going to tell you about the Kardar-Parisi-Zhang or KPZ universality class. And before starting the lecture, let me first express my gratitude to all organizers of this school, and in particular, Yamagishi-san, who is chairing this session and who really took great care of many things for my lecture. And I'm so impressed by the quality of the organization, and that made me particularly happy to give a lecture in this school. Okay, and to the audience, let me announce a few things on the lecture. So first, as Yamagishi-san announced, I will use Slido and also Zoom chat box to take questions. So as Yamagishi-san emphasized, any questions are really welcome. So you can ask questions anytime during the lecture. And as I said, you can ask either by Slido or Zoom chat box if you want to type your question. But actually, if you can use Slido, that might be better because actually I prepared window like this. So if you type your question on the Slido, your question will be displayed on this box immediately. Maybe I can use this kind of thing. I bought it from Amazon. All right. And actually, I'm opening a poll in Slido. So if you access Slido from this QR code, maybe you are seeing the poll. But if you want to ask questions, you can click audience Q&A or something like that. And then I think you can ask questions. So let me try myself. Does it work? I think
it's working.
Oh, yes. Okay. There is some time delay. I see that.
Yeah, but are you... So maybe you want to switch recent and popular for Q&A?
I'm not sure which is good, actually. So,
Okay.
Okay, probably recent. Yeah. So, okay.
It's up to you. We can just pick up questions.
Okay, I switched it to recent. Okay.
Okay. Thank you.
Yep. Okay, so anyway, your question will be displayed here, and you can ask question without showing your name. So probably that's an advantage of Slido. And as I said, you can also ask question by Zoom chat box, but since it will not be displayed, it could be that I just don't notice. And if that happens, I hope Yamagishi may help.
Yeah, I will.
Yeah. Okay, and also you can of course unmute your mic and ask questions orally, and that's also welcome. And probably that's the quickest way to ask questions. In any case, I appreciate such interactions with the audience. So please don't hesitate to ask any questions. And secondly, you can download my slides of the lecture from this URL. And of course, you can also use this QR code and you get the PDF. And there is also a list of references that I cite in my lecture slides. And that is a separate PDF, and you can download it here or from this QR code. Okay, is there any question up to now? And if not, let's start.
May
Yamaguchi-san,
I
okay?
ask
Yeah.
actually one? Yes,
Sure.
yes, but may I actually ask one question? So are we allowed to write something not really relevant to lecture on Slido, like a
Yeah.
hi or something?
Yes. Yeah,
Okay,
you can go
okay.
ahead. Yeah. Yeah,
Thank you.
it's probably a nice idea to make the lecture more, you know, yeah, active.
Yeah.
Yeah, that's maybe, yeah, that's great indeed.
Okay, thank you.
Yeah. Okay, so let's, oops, yes. So the next thing is actually, I use the Slido function for opening a poll. And I just want to know the expertise of you. So I understand that this school is multidisciplinary. So, well, it is about physics, but there are many branches of physics. So you are coming from very diverse areas of physics. So please access to the Slido page if you want. I mean, if you can, and just let me know your field of expertise. And I'm glad that someone already answered nonlinear physics. That's also my expertise. And myself, let me also vote. Myself, I'm doing statistical physics, experimentally.
Excuse me.
Yes.
We hear you, but did you go to the next slide? I mean, your video is not working
Oh, okay.
now. It
Okay.
stopped.
That's bizarre. Yeah.
Oh no, it's
Okay.
yeah. It's I guess it's
Yeah,
the next slide.
something
Yes.
happened. Sorry. Yes. Thank you for letting me know. Yes. Yes. So my expertise is statistical physics, and I'm doing statistical physics experimentally. And you can also answer multiple times. So in terms of material, I'm using soft matter systems. Oh, yes, soft matter physics. But I found that someone answered soft matter. So I think I can join that, or maybe that's not possible. So I confess that I'm not also so used to Slido actually. Oh, okay. Soft matter became a big group. Okay, so I'm seeing that there are at least a couple of audience who are working on soft matter physics, non-equilibrium phenomena, but it could be that they are from my lab, actually. I don't know. Otherwise, I see glassy matters, economic physics, cold atoms, critical phenomena, one-dimensional conductor, and condensed matter. Okay, that's very nice. So I do have participants from diverse areas of physics, and that's also why I want to give a lecture in this school, and also why I chose the KPZ universality class, because as I will explain, the KPZ universality class is expanding the scope more and more to many different areas of physics and even beyond. So I wish I can explain that during my lecture. Okay, so let me close this poll for expertise. Yes, now it's closed, and I'd like to focus on this Q&A session. Okay, so let's start. So before starting the content, I'd like to introduce the background and what I'm going to tell you about during the lecture. So first of all, let me give you the background of the subject. And myself, I would put the physics of the KPZ universality class in the context of physics of critical phenomena and scaling laws. And as many of you know, the physics of critical phenomena was built and in statistical physics, and it was done so not only by theoretical breakthroughs such as Onsaga's exact solution to the 2D Ising model, but experiments also played significant roles. And that includes discovery of the liquid vapor critical point. And also experiments found that diverse phenomena such as magnet, alloys, and binary mixture of fluids may show the same critical exponents. And that kind of prehistory on the physics of critical phenomena led to the foundation of the renormalization group theory by Kardar and Wilson. And that established the concept of the universality class. And that was done on the basis of continuum equations, such as the FIFO model. And that was not the end of the story, but physics of critical phenomena has continued to develop even today. And of course, all these are about critical phenomena at thermal equilibrium. And here, the major player was the Ising model and its universality class. Now, if we turn our attention to systems driven out of equilibrium, although it is far less developed, I would say the major player is actually the KPZ universality class. And that is because we are making similar steps, similar to the physics of equilibrium critical phenomena. I mean, there are major breakthroughs, both from theory and experiments. And that includes the foundation of a continuum equation, which is called the KPZ equation. And there are also exact solutions, and main predictions from exact solutions were also tested experimentally. And recently, the scope of the KPZ class extended. So it was first developed in the physics of classical systems, but now the scope of the KPZ universality class even extended to quantum systems, notably the Heisenberg spin chain. So it is relevant in various areas of physics. And that diversity and the deepness related to the exact solution, in addition to the importance for physics of non-equilibrium critical phenomena, those kind of things are exactly why I believe KPZ is worth learning for all areas of physics. Okay, then let me describe the phenomena. What kind of phenomena are described by the KPZ universality class? As I suggested, there are many phenomena that are believed to be described by KPZ, but the most representative is growing interfaces. And let me show you an example. This is a video showing accidental fire of popular flags. And this video was taken in a park in Spain. And what is remarkable here is that we can easily see an advancing fire front. And this front separates the two regions that are already burned and yet to be burned. So that front is something we are going to call our interface, and particularly our growing interface. And importantly, such an interface is not a simple line, but it is fluctuating. It has a very complicated structure, yeah? And that comes from randomness in the time evolution rule. So we can ask what kind of fluctuations they are. For example, how the amplitude of the fluctuations depends on time and whether it is Gaussian fluctuation or something more exotic. And that is a non-trivial question because such fluctuations are strongly correlated. And this is a nonlinear phenomenon and of course, non-equilibrium. And of course, such fire spreading is not the only example. Myself, I use liquid crystal, more precisely turbulence of liquid crystal, to realize such a glowing interface, as you can see here. And we do observe similar fluctuations of the interfaces. There are also examples of colloidal particle deposition, cancer cell growth, and so on. And in such controlled experiments, we can compare with theoretical predictions from the theory of KPZ class. So what kind of predictions are there? Of course, this is what I'm going to explain in this lecture. So this slide is just meant to show you a kind of preview, yeah? And here I like to show that preview with my experimental data. So in my experiment, I had cluster of turbulence growing from a single point. So this produces a circular interface expanding in the radial direction. And predictions on the KPZ class are about fluctuations of the interface that you see here. So to characterize that, we take the local radius denoted by h, which is the radius taken at each angular position. And it is a function of the position of the angular, so it is a function of the angular position x and time t. Then we can simply define its fluctuation, delta h, by the difference from the average. Then the theory of the KPZ universality class predicts a power law that the amplitude of this delta h grows like t to the beta. And this exponent beta is a non-trivial exponent, and that is universal. And for such one-dimensional interfaces, the value of the beta is known to be 1/3 for the KPZ universality class. But more importantly, theoretical developments of exact solutions on the KPZ class established, for example, what kind of distribution we see here. And surprisingly, the distribution of such interface fluctuations is not Gaussian, but it turned out to be a distribution known from a totally different area, that is random matrix theory. So we have a deep connection to such apparently unrelated fields of science, and such non-trivial theory can be confirmed quite precisely by experimental data, as you see here. And as I already mentioned, the glowing interface is not the only target of the KPZ class. There are a great variety of phenomena and theoretical concepts that are relevant in physics of the KPZ class. And the scope is expanding even right now. And related phenomena include stochastic particle transport, sudden polymer problem. And there are also examples in quantum physics, such as the exciton-polariton condensate, Anderson localization, and quantum spin chains. And there are also many theoretical concepts involved, not only universal scaling laws, but also physics of integrable systems, random matrix theory, and so on. And in this lecture, I plan to explain how such connections to diverse areas are made. And for the keywords that are highlighted by green color. And in particular, near the end of the lecture, I like to illustrate the connection to quantum spin chains. And this is one of the latest topics in KPZ. It is about anomalous hydrodynamics of spin transport in quantum integrable systems. And I will explain recent theories and experiments which reported this surprising connection to KPZ. I will also give some critical comparison with KPZ for classical systems and mention an open problem, which I'm happy to think about with interested audience. So this is the lecture plan. The aims of the lecture is that I'd like you to understand, I'd like to tell you what is the KPZ class at all, and how connections to different systems are made, and also the main outcomes of the modern developments of the KPZ class. And when I explain modern developments on the KPZ class, my purpose is to foster intuitive understanding of the outcomes rather than explaining technical and mathematical details. So I will not enter such details, but I like to emphasize what kind of predictions are made and how connections to different systems are made. Okay. So this is the table of contents. We are here about the lecture. And first, I will explain how to describe growing interfaces in general. And I'd like to explain a few universality classes defined in that context. And then I'm going to focus on the KPZ universality class, which is characterized by the KPZ equation. So I'll explain basic properties of the KPZ equation. And in the latter half of the lecture, I will describe exact solutions for the 1D KPZ class. And finally, I will describe recent surprising connection to KPZ in quantum spin chains. And of course, I cannot cover everything on KPZ class during the 3 hours of this lecture. So I also made a list of recommended reviews on KPZ. And my lecture is basically based on my own lecture notes I published in this journal. So again, you can download the list of references. So these numbers in the bracket, the reference number, and there is a hyperlink in the reference list corresponding. So you go to number 10, for example, and you can click the title of that paper, and you can go to the journal page. So you can easily access the every reference I mentioned in my lecture. And there is a kind of Japanese version of my lecture notes, which is published here. So those are my reviews on this context, on this subject. And about reviews written by other authors, I classified them into two. So for the physics of KPZ, the year 2000 is special because in this year, exact solutions were found. So before the year 2000, there's no description on the exact solutions. But still, there are many important physics described there. And that is still the basis of the physics of KPZ right now. And there are many review papers and textbooks written before 2000. And among them, I would recommend them. And after the year 2000, where exact solutions were established, there are many papers mainly written by mathematical physicists. The first one is written by a mathematician, Ivan Colvin, and this is one of the most complete review papers from the mathematical side. And for mathematical physics side, I would recommend number 17, and also a short review paper written by Sasamoto-san is a great introduction. Okay, yes, I'm happy to see someone liked the reference list I made. Thank you for your comment. Yes. Okay, so I think that's all about the chapter 0. Okay, do you have any question up to now? If not, let's start the first chapter. So in this chapter, I will describe how we can, I will explain how we can describe growing interfaces and universality classes. And then I found one question: why does turbulence look dark? Okay, I'm happy to explain that. So I think you asked about this. Oh, sorry. Yes. So I think you asked about this growing turbulence. This is a turbulent state of convection of liquid crystal. We actually use electric field to drive the convection, and for high applied amplitude, we can observe this growing turbulence. And this turbulence actually consists of many topological defects. In liquid crystal is characterized by orientational order. So liquid crystal molecules align themselves like this. So if everyone is aligned in the same direction, it corresponds to the lowest energy state. But in reality, there are some topological defects about this orientation order. So the orientation of liquid crystal may be rotated around a topological defect. And in this black turbulence, there are many such topological defects. And if there is a topological defect, it can scatter the light. And in this experiment, we are observing the turbulence by transmitted light. So the black region scatters more light, and the incident light becomes weaker. That's why this turbulent state looks dark. And we can easily distinguish this region and the outer region by image analysis. And that's how I analyze the fluctuations of the interface. Okay, yeah, it's my pleasure. And by the way, convection is indeed Taidu, yes, and turbulence is Landu. Okay, very nice. Then let's start the chapter 1. So again, in this chapter, I'd like to focus on such growing interfaces. And one thing I should emphasize here is that those examples are microscopically very different systems. Yeah. Fire combustion is a complicated phenomenon related to chemistry and of course physics and convection. Liquid crystal is a totally different kind of system. And this is a deposition of colloidal particles in a suspension. So each system is described by a very different kind of physics. So in principle, we cannot expect something in common. But at least if we see those videos at macroscopic level, there seems to be something in common. So in all cases, we see growing interfaces, and interfaces are fluctuating. And the fluctuations of the interface are, qualitatively speaking, similar in the sense that there are many length scales involved. And in a very sense, interfaces may look something similar to fractal. So microscopically, they are totally different, but macroscopically, we may expect something more general, which can include all these examples. So we would like to focus on a coarse-grained description on such growing interfaces. So the idea is that what kind of symmetry exists there, and what kind of terms will be important to describe that kind of interface. To explain that, let us start with a very simple toy model. So I like to use particularly this kind of deposition problem. So here, particles are falling from top of the video, and they are accumulating on the substrate, kind of. So this is a very naive toy model on that kind of deposition process. So suppose you have a substrate, and for simplicity, we consider a lattice system. Okay, so the coordinate x is discretized, and you randomly choose a site. Okay, you choose it randomly anywhere, and you just drop a block from top. Okay, so this is the illustration, and a block just falls until the to the bottom. So if there is no block on this side, this block just goes to the bottom. If there are already some blocks, then this newly added block will arrive on top of the highest block. Okay, and we just do everything randomly. So we drop a block randomly at a constant rate. So I drop a single block per unit time, let's say, at random positions. And blocks just accumulate. There is no interaction with neighboring sites. So each site is statistically totally independent. The definition is clear. Then the problem is very simple. We can so we define the height h by just the number of blocks we have on each side. So here h is 3. Here it was initially 0, but after this block fell, the height increased to 1. Okay. Here h is 1, h is 0, and so on. This is my definition of h. Then it's easy to realize that the average of this h grows like t, because I drop a single block per unit time. Okay. Yes, so mean h is proportional to t. Then what about the fluctuations? Of course, the fluctuations are characterized by the variance, for example. So let me define the fluctuation. Delta h is h minus mean h. And for this simple example, it's easy to find that delta h grows like t to the 1/2. And this is simply a consequence of the law of large numbers. So by definition, during unit time, each site has a chance of growth by one unit, yeah? But that is random number. For a given site, we don't know if the next block will come to this side or somewhere else. So at each time step, you have a chance of growth by 1 unit, and that is regarded as a random number. And then the height at time t is just the accumulation of just the sum of such random numbers provided at each time step. Can you imagine that? And since we do everything without any correlation in this process, but we can safely use the central limit theorem and the law of large numbers. So the variance of h will grow like t. So the standard deviation will grow like t to the 1/2, and the distribution is Gaussian. Okay. Now, I'd like to describe this process by a continuum equation. So we want to coarse grain this system, and I like to redefine this height h as a function of a continuous space x. And then I like to think about the partial differential equation to describe this h in the continuum space. So what we will have in this in the right-hand side of this partial differential equation is the following. First of all, the mean height will grow in proportion to t. In other words, there is some mean speed of the growth. So suppose that let v naught the speed of such mean growth, then we should have such a constant term in the right-hand side. And then we of course have fluctuation. And that fluctuation is a simple uncorrelated random number. There is no correlation in space, no correlation in time, and thanks to the central limit theorem, the distribution of such a random number is the Gaussian noise, is the Gaussian distribution. So because of the absence of correlation, this ether is a white Gaussian noise, and the mean value of the ether can be said to be 0. And that's because we already put the growth speed of the mean height here. So the mean of ether is 0. And the variance can be described by this by using delta functions here. So this is just to say that there's no correlation at two different positions in space. And there's no correlation between 2 times t and t prime. And the amplitude of the this covariance is given by a parameter d. Is it clear up to now? And about the word, coarse grain is, I think, more popular translation is 素子化ですね。コースグレインっていうのは素子化するということですね。But thanks anyway. Okay? Okay, so this is a toy model. And that's a trivial example because there's no interaction between sides. Now, what happens if there is interaction? As the simplest kind of interaction, let's consider some kind of relaxation on the surface. So the definition is very similar to the previous trivial example, but now when a block arrives at the top surface of the interface, it can slide to the next to the neighbor if the neighbor is lower than the site of the interest. So for this example, this block arrived here, but since its two neighbors are lower than this site, it can slide in either direction. So probably we can choose it randomly. If left is chosen, then this block slides here and falls up to here. And that happens only when neighbor sites are lower. So for this block, it arrives here. And since its neighbors are higher than here, there is no slide happening. Okay. And you don't need to apologize. It's okay. I'm totally happy. And I also got a question about the boundary condition. Yes, thank you for this question. I omitted. Physics of the KPZ class is basically for large systems, infinitely large systems. So of course, the boundary condition is important for some context, but in many cases, the boundary condition does not give a direct influence on the result that I will explain in this lecture. So that's why I omitted. But of course, to do simulations, we need some boundary condition. So the easiest choice is you introduce the periodic boundary condition. So if you have L side, and then for the leftmost side, your left neighbor is the rightmost side of your system. That is an example of the boundary condition you can choose. Okay. Okay, so we introduce such a surface relaxation of the blocks and see what happens. First, if we do simulation, it's easy to guess that such relaxation will smoothen your interface to some extent. Yes. So this is a comparison of the case without surface relaxation. So this is the trivial model I explained in the previous slide. And this is the model with surface relaxation. And I compared, I plotted 3 snapshots taken at different times. And the times are the same between the 2 panels. And you can immediately see that indeed, the fluctuations are smaller if you have surface relaxation as expected. But still, it's not perfectly flat. You have fluctuations, and those fluctuations are already not so trivial. It's, let's say, non-trivial. Okay, then what kind of continuum equation we can use for this problem? We can start from the same equation I explained in the previous slide, but of course we need to introduce a term that corresponds to this surface relaxation. And that is the diffusive term, like this. If you want some derivation, you need to consider a flux of block. And flux is, flux goes to the lower side. So very roughly speaking, the flux of particles is proportional to the gradient of height, gradient h. And then you take the divergence of the flux and you get the right-hand side of this partial differential equation. So if you take the divergence of the gradient h, you get this Laplacian term. Okay, so this partial differential equation with this Laplacian term is expected to be a continuum equation for describing this process, and it is called the Edward-Wilkinson equation. Now, can this equation describe the fluctuations we see in the simulation?
Excuse me.
Yes.
I might have just missed, but what is new?
New here?
Yes.
Oh, sorry. This is just a constant parameter. Okay. So when we derive that, we consider the flux of the particles, and I just in the lowest order approximation, the flux can be regarded to be proportional to the gradient h. So if I take the proportionality constant nu, so how can I sorry? Oh, I cannot use okay. I expected I can use whiteboard from iPad, but maybe not. Maybe my version of Zoom is old. Anyway. Okay. So let me try to. Yes. Yes.
Are you now
please.
able to use whiteboard? No.
I don't think so, but
Oh, I'm
well,
sorry.
on my computer, I think I can do that. Maybe not. Anyway, that's not a problem. Sorry. So the short answer is it is just a proportionality constant. We don't know how the flux and the gradient h is related. I mean, we can expect that it is proportional, but we don't know the proportionality constant. So I just define it to be nu. And then this is a coefficient that appears in this in this term.
Okay, so it's just a constant, like,
Just a constant.
determined by experiments or something.
Right.
Okay, thank you.
Yeah, thank you. Okay, so we have this Edward-Wilkinson equation, and then let me give a few remarks on this equation. First remark is that we introduced this constant term V naught as the mean speed of the interface, but mathematically speaking, we can immediately notice that V naught can be omitted safely by changing the variable h by this. Yeah. If you replace h by the right-hand side of this, I mean h prime plus V naught t, then this V naught can be erased. Physically speaking, we can ride on a co-moving frame that is moving with the interface, and then the mean speed vanishes. So we can safely erase it. And in the literature, we often find the Edward-Wilkinson equation without such a constant term. And second remark, and the most important thing is, of course, what kind of fluctuation this equation shows. So what kind of scaling laws we have here? To see that, we suppose that solutions of this Edward-Wilkinson equation are statistically invariant by scale transformations. So very qualitatively speaking, the structure of the interface we see here has many different length scales. Some fluctuations are small, other fluctuations are wider. There are many scales involved, and it could be that it is scale invariant. The meaning of the scale invariance is that if we zoom a small piece of interface, if we take a small piece of interface and just zoom it, and then that zoomed interface may look similar to the entire interface. That is the meaning of the scale invariance here. And if I use equations, suppose I change the coordinates x, time t, and delta h as follows. So I define the new coordinate variable x prime by just putting some constant factor here, which is b. So I change the scale of the space. And according to that scale change, I also change the scale of time using the same factor b, but this factor does not need to be the same as the factor here, so I put some exponent here. And I do the same thing for the scale along the h-axis. And since we are interested in the fluctuation, we transform delta h by like this. In this way, I introduced two exponents, z and alpha. Okay. And I got a question about the definition of delta h. This delta h is, yeah, I'm sorry for this maybe it was not very clear. So delta h is h minus mean h. And it is not standard deviation for the moment. So yeah, so in other words, I just changed the variable h itself. So this h, maybe I didn't stress enough, but this h is a random number because we have random number in the time evolution equation. H is random number. And mean h is at least for this example, it's clear that the evolution of mean h, you take the average on both hand side, and this eta disappears, and you see that mean h grows. The time derivative of mean h is just v naught, so mean h grows like v naught times t. And then this delta h is just h minus mean h, so h minus v naught t, and delta h itself is therefore a random number. But we can still think how the typical amplitude of that delta h grows in time, and this is what we want to describe by this scaling law. I mean, by the scaling law that I will show in the next slide. Okay, is it a bit clearer now? Okay, let's proceed. So we want to do this kind of scale transformation, and the purpose is that we want to find such a value of z and alpha that the fluctuation properties of delta h prime are identical to those of delta h. Okay, and okay, and this is what we want to do. And if we can find such values of alpha and z, then we can know how the fluctuation delta h grows with time. So oh, 注釈. Oh, I see how I can draw with my iPad. Okay. So we have, oops, yes, delta hxt. It looks very weird on my display. And we define this. And suppose we fix t prime. So t prime, yes, t prime is fixed. Suppose I fixed it. And then B, we have yes. We have this, and t prime is fixed. So my B is proportional to t to the 1 over z. Okay. And I insert it here, and I get t to the alpha over z times some delta h. And since I fixed t prime, the fluctuation properties of delta H prime are independent of time because my time is fixed here. So my delta H here is proportional to T to the alpha over Z. And we get this equation, okay? So anyway, the message I wanted to tell you here is that, that once we find such values of Z and alpha, that the fluctuation properties look identical by this scale transformation, we can know how the fluctuation grows with time, okay? And I got question, in random deposition problem without relaxation, why the noise is Gaussian in spite of the monotonicity of the H of X and T? Yes. Of course, that is a good question. So, in fact, here I coarse grain not only in space but also in time. So, suppose at a very small time scale, time step delta t. Okay, so to describe this kind of process more precisely, let me redefine as follows. During a time step delta t, there is a probability p times delta t to drop a block. So I don't always drop a single block, but there is a probability to drop a block during a short time step delta t. And that probability is proportional to delta t, okay? And at each small time step, the height changes by 1 if the block is dropped, okay? And then after many such time steps, your H is created. And when I coarse grain to get the partial differential equation, in my time unit is already large enough compared with the small time step. So for the so let what is a good way to say that? So of course the partial differential equation can be discretized. And to define the partial differential equation, we start by considering a finite time step, but that time step used to define this partial differential equation is already big enough compared with the time step I considered here. So during the time step here, I already have many accumulations of the random numbers. So that random number can be taken to be a Gaussian random number thanks to the law of large, thanks to the central limit theorem. And of course, it should be positive by definition if I don't have this V naught. But since we took this V naught, I mean, we took the mean growth speed as already here. The mean of this ether is 0. So this ether can be either positive or negative. Both are fine. For this ether, this is a fluctuation relative to the mean height of the interface. That's why it can take both positive and negative. Is this, did I answer your question? Okay. Okay, so this is what we want to do. And if I just do this program, so I remind you that I like to do this scale transformation. I insert this X here, this T here, this delta H you can subtract mean h here, and you can apply this scale transformation to h here. And then the first term on the left-hand side gives b to the alpha minus z, b to the alpha from h, and minus z from this t. This should be equal to b to the alpha minus 2. Alpha comes from this h, and minus 2 comes from this second derivative. And from this eta, eta is defined by this. So if you do the scale transformation for x and t here, then you actually get b to the minus d plus z divided by 2. And all these changes in the coefficient, I mean, all these extra factors should be equal in order for this delta h prime to be statistically identical to the original delta h. So these are connected by equal, and from this we get this scaling relation. And this d is a space dimensionality, and for one-dimensional interface, we can see that beta is 1/4. So it means that for the Edward-Wilkinson equation, delta h grows like t to the 1/4. So already with this Laplacian term, the scaling exponent beta has changed. Yeah. From this simple random deposition, it was 1/2, but thanks to the diffusion term, it became 1/4. Okay, so far it looks good, but in fact, this Edward-Wilkinson equation is not a very good model to describe real phenomena. And that is because we use this axis h to describe the interface. And by definition, h is taken perpendicular to the substrate we have. It means that the interface tends to grow upward no matter the shape of the interface. So even if the interface is bent like this, the interface tries to grow always upward. But probably a more natural way for this interface to grow is just to expand like this. So it's more natural for the interface to grow perpendicularly to the local inclination of the interface. And to take into account this this growth direction, we need to change the variable. So suppose at each point we have local h variable and local x variable here. For example, h is perpendicular to the interface and x is parallel to the interface. And suppose at each local point, the interface grows according to the Edward-Wilkinson equation. So this h local and x local are the variables of the Edward-Wilkinson equation. And then we transform it to the global axis h, which is always taken upward, and x is always taken horizontally. And to do this transformation, we use this angle theta, which is defined by arctangent of the gradient h. And then this dh is dh local divided by cosine theta. And by using the gradient h, it looks like this. Then we just keep the lowest order nonlinearity. So this square root of 1 plus gradient h square is just dh. So this square root transforms to 1 plus 1/2 gradient h squared. And that gives this additional term proportional to gradient h squared. And this equation is called the Kardar-Parisi-Zhang equation. after the 3 people who first written down this equation. And this KPZ equation is known to be a generic equation for describing this kind of random growth processes. And it is the most important, well, simply speaking, most important equation for growing interfaces. And as I will explain later, for one-dimensional interfaces, again, so not only for 1D, but in general dimension, this term is known to be relevant. So it changes the scaling exponents. And for one-dimensional interfaces, it's known that the exponent beta is now 1/3. So the amplitude of the fluctuation grows like t to the 1/3 for the one-dimensional KPZ equation. And those exponents are known to be universal. So it is not only for the KPZ equation, but for some group of interfaces, this set of the exponents is commonly observed. For example, the liquid crystal turbulence, the colloidal deposition, and fire front, not of course in the Spanish Park, but in some controlled experiment, all these experiments actually showed the same set of exponents. So this is universal. And that group of systems showing the same universality, same exponents is called the KPZ universality class. All right, and let me give you some remarks. First remark is the same as the one I already gave. This V0 can be omitted by the scale transformation. By this Galilean transformation. Second is the symmetry. Symmetry is always important in physics, and the KPZ equation has this set of symmetries. So KPZ equation is invariant under time translation, space translation, space inversion. For example, x can be flipped to -x, but still the evolution looks the same. And we also have high translation. And this high translation is actually important. This forbids having a term like -AH. And if you are familiar with the Ginzburg-Landau theory for critical phenomenon, we can describe the time evolution of the order parameter by an equation to some extent similar to that. We don't have gradient h squared, but we have Laplacian term. And for the Ginzburg-Landau equation for critical phenomena, we also have a term like -a times order parameter. And this coefficient A is proportional to T minus Tc. And then apart from the critical temperature Tc, we have this kind of term for the Ginzburg-Landau theory. And in that case, we don't have scale invariant fluctuations. So scale invariance is a special property only observed at the critical point. This is the case of the critical phenomena. However, for the KPZ equation, because of this high translation symmetry, a term like this is forbidden. So in a sense, we are always at the critical point, and we have scale invariance without any kind of fine tuning. So that's why a concept like similar to that of the critical phenomenon is valid in the physics of the KPZ equation and growing interfaces. Okay. And the next remark is that although I introduced the KPZ equation on the basis of this kind of argument, but actually this is merely one way to derive the KPZ equation. KPZ equation is more general than this kind of situation, and this can arise generically even if we don't have isotropic growth that I considered in this argument. So one such example is again a kind of deposition model called the ballistic deposition. So in this model, you drop a block, but the block falls like this, and there is no surface relaxation in this model. But a block can stick to the neighbor if there is a neighbor at higher than the height of the position of the drop. So this block falls, and whenever it finds a neighbor, then it sticks here. This is the definition of the ballistic deposition model. And this model is known to show the exponents identical to the KPZ equation. So this exponent is observed in that model. And this model obviously does not have isotropic growth. The growth is not isotropic, but still the KPZ, universal fluctuations of the KPZ class are observed. So the message is that KPZ class is general. Many growing interfaces have this kind of symmetry and nonlinearity, and then the KPZ equation is the most probable case that may describe such growing interface. All right. Okay. Do you have questions up to now?
Can I
Yes.
ask? I'd like to know why nu and lambda do not relate to the scaling exponents. So, do we able to can we normalize those?
Could you? Sorry, I'm sorry. Could you repeat again your question?
I want to know why the constants nu and lambda do not relate to the exponents.
Oh, so your question is why this constant nu and d are not renormalized?
Yeah.
Okay, that is a very good question, and that is not trivial actually. So in the case of the Edward-Wilkinson equation, so I just I didn't go into that precision, and I just assumed that nu and d are not renormalized, and I just try to apply this scale transformation, and I find this set of equations. And by renormalization group calculations, we can show that this is the right answer. But this is not true anymore for the KPZ equation. If I do the same thing for the KPZ equation, then actually we don't find this answer, but something different. So to find the correct exponent for the KPZ equation, we need to do careful calculation of the dynamic renormalization group. And then we will find that only lambda is unrenormalized. And the other parameters like nu and d here are renormalized. So they cannot be regarded as constants. And that is related to symmetry. And I'm going to explain that in the next chapter.
I see.
Thank you.
Thank you.
Okay, and I also got another question. Are there other theoretical continuum models or other universality classes? The answer is yes, there are many. And I just skipped them because I don't have enough time. One such example is quenched KPZ class. So here, I assume that my noise term is a function of x and t. So noise is fluctuating in time as well, not only in space, but also in time. But in some experimental systems, noise may not depend on time. For example, in the fire spreading process, the source of fluctuations is depends on the noise appears because some places on the ground are more easily burned and other regions are less easily burned. So in a sense, the noise we have here does not depend on time, but it depends on the position only. So to describe that kind of process, it's more realistic to consider eta as a function of x and h instead of t. And that equation is called the quenched KPZ equation. Such a noise that is independent of t is called quenched noise in statistical physics. And the quenched version of the KPZ equation is called quenched KPZ equation, and that is known to form another universality class. That is one universality class relevant in, especially in experiments. And there are a few other universality classes corresponding to different symmetries or conservation laws. And if you are interested, I recommend you the textbook by Parapasi and Stanley. I think it is reference number 10. Oh, sorry, yeah, 12. I forgot, 12 probably. Okay, welcome. Are there the questions? Okay, for some reason, this display is always showing previous questions. Okay. If not, let me go to the chapter 2. Okay, in this chapter, I'd like to explain some basic properties of the KPZ equation. And here we start to see, so, okay, one main purpose is we would like to derive the scaling exponents I showed here. This can be derived exactly for 1D without using the exact solutions developed from 2000. So it is rather simple argument. We only need a simple argument related to symmetry to derive this set of equations. So let me explain that. And in the course of enduring that derivation, we start to see some connections to different problems in physics. That's another purpose of this chapter. Okay, let's go. First, I'd like to explain relation to another equation called the noisy Vargas equation. It is an equation from fluid mechanics. So we start from the KPZ equation. And as I already said, this constant term V0 can be erased. So I just want to erase from the beginning. Okay. Now, let's take the gradient of this equation. I just apply gradient for both hand sides. And I like to define a new variable V, vector V, just as the gradient H times minus lambda. Lambda is the coefficient here. Then you can easily find this equation. I mean, you just do this and you find this. This is an equation called the noisy Vargas equation in fluid mechanics. If you know the Navier-Stokes equation in fluid mechanics, then the left-hand side looks exactly like the Navier-Stokes equation. Yes, this term is called the convective term or advective term. And for fluid mechanics, this Laplacian term comes from the viscosity. And the last term corresponds to the external force to the fluid. And here we have gradient eta, and eta was a random number. So this corresponds to the case where we have some random forcing to the fluid. And for the real fluid mechanics problem, we also have a pressure term, and that is how the Navier-Stokes equation looks like But in the Vargas equation, that pressure term is neglected. So it is not a good model for fluid mechanics, actually. So it is often called just a toy model, which has nothing to do with many problems in fluid. But still, it can be an interesting model in fluid, and it tells several things. So it's always it's often considered in fluid mechanics. Anyway, so and also one more thing is that Vargas equation is studied a lot in the context of soliton waves and integrable systems. And it is a model equation for describing shock waves on the fluid. Anyway, so the message I wanted to tell here is that the KPZ equation is equivalent to this kind of fluid mechanics equation with random forcing. And a consequence of that is that the first consequence is that it has a symmetry expected for fluid mechanics problem. And the most representative is the invariance under Galilean transformation. Suppose you are riding on a flame moving at a constant speed v0. Sorry, this v0 vector has nothing to do with this v0. It is another constant vector. Suppose you are riding on a flame moving at this speed v0. Then on this moving flame, the fluid mechanics should look identical to the original flame. And that is the Galilean symmetry. And it is expressed by this transformation. This is Galilean transformation. And the Vargas equation is invariant under this transformation. And this is a fundamental symmetry of the fluid mechanics. So it should be kept as it is, even if we change the scale of description. So Galilean symmetry should be kept as it is under the scale transformation. And the consequence of that is that advection term here is non-renormalized. So in fact, this Galilean symmetry is guaranteed thanks to the convective term here. And in order for the Galilean symmetry to be satisfied, this coefficient must be 1. It means that even after scale transformation, this coefficient needs to be 1. So it is non-renormalized. Okay. Now, let's consider a different definition of V. Instead of using lambda here, I'd like to redefine V without lambda. Okay. I don't have lambda here now. And then the resulting equation is, of course, very similar, but the parameter lambda is, this lambda is absent. And instead of that, we have lambda on the convective term. And we have just seen that this convective term, advection term, is non-renormalized. This means that this parameter lambda here in the KPZ equation is non-renormalized. And this is thanks to the Galilean symmetry, which can be seen by this transformation. I mean, this can be seen by this mapping. Yeah. Okay. So this lambda is invariant under scale transformation. And from this, we can get one scaling relation. Let's apply the scale transformation that I already introduced, okay, to this equation. And we want to compare the left-hand side with this gradient square term. from the left-hand side, we get b to the alpha minus z. From this term, since lambda is not renormalized, we just have alpha minus 1 twice. Yes. And this must be balanced. From this, we get this simple scaling relation, alpha plus z equal to 2. And importantly, this mapping is valid for any dimension d. So this is a very general scaling relation for the KPZ class. Okay. Okay, so this is what we can learn from this mapping to the noisy Vargas equation. Next, let me also explain the stationary state of the KPZ equation, or one-dimensional KPZ equation. To explain that, let me give a few words on the Langevin equation and the Fokker-Planck equation. Langevin equation is a time evolution equation, or kind of equation of motion for a particle that is driven by some random force. So this is a time evolution equation. So suppose this capital Xi is the coordinate of the particle we consider, and time derivative of that is driven by some force. And in the Langevin equation, we also consider that there is some noise term to this time evolution equation, and that noise term is eta I. And for simplicity, we consider the Gaussian noise, and the mean value is 0, and the Gaussian, the covariance is said to be like this. Again, there is no correlation. It is white Gaussian noise. So we have a delta function here, and the index I is actually the index for particles. Suppose we have different particles, multiple particles, and each particle is subject to random noise that is independent from each other. So we have Kronecker delta here on the particle index. Okay, so this is the Langevin equation. And this capital Xi is a random number, random number that describes the position of the particle. And there is another way to describe this kind of stochastic process. Instead of using the coordinate of the particle directly, we can think about the probability distribution of this Xi. So suppose, so let P of, by the way, this curly Xj is a set of all coordinates x1, x2, x3, up to some xn. So this curly Xj is a set of all particles' positions. And then we consider the joint probability of those particle positions at time t. And we can, instead of considering the time evolution of the bare xi, we can equivalently consider the time evolution of the probability of those xj's. And if you open the textbook on stochastic processes, for example, the one cited here, then you can learn that the time evolution equation for this probability density is given like this by using the terms we have on the Langevin equation. So this Fi is the deterministic term of the Langevin equation. And this D here is the noise amplitude we have here. And this time evolution of the probability density is called the Fokker-Planck equation. And again, I stress that this Fokker-Planck equation is equivalent to the Langevin equation we have here. So we can choose description more convenient to the for our purpose. Okay. And then this is about set of finite number of particles. So we have index I. But we can also formulate a partial differential equation version of the Langevin equation. So instead of the particle position xi, suppose we have a field h. So this is a function of continuum space and time. And suppose we have a partial differential equation like this. For the right-hand side, the first term contains all deterministic terms in the time evolution equation. And the second term is the white Gaussian noise that I introduced in the previous chapter. Okay. So this is a kind of time evolution equation we have for growing interfaces. And then we can also derive the corresponding Fokker-Planck equation. And that Fokker-Planck equation looks like this. And we can derive this from this. So suppose we discretize the continuous space X. So we consider lattice, for example. We have position X1, X2, X3, and so on. And then H at X1 can be regarded as this capital X1. H at X2 can be regarded as capital X2, and so on. And then the discretized version of the Langevin PDE is nothing but the multiple particle version of the Langevin equation. And we have the Fokker-Planck equation. So by taking the continuous limit, we obtain this. And here we have this special kind of derivative, which is functional derivative. And formally speaking, this functional derivative can be read as this. I think you encounter this kind of functional derivative in the analytical mechanics. I don't know how to say in English. 解析力学. There's a question about the PDE. PDE is partial differential equation. Sorry for that. I didn't say. Okay, so anyway, the message is that we can rewrite the Langevin PDE, that is a kind of time evolution equation we have for growing interfaces, to the corresponding Fokker-Planck equation. Okay. Okay, so let's do that. For the Edward-Wilkinson equation, the equation is this, and of course the deterministic term is the first term, and the rest is either. Then I just inserted our f here to here, and we get this Fokker-Planck equation. Okay, and then we are interested in the stationary state here. Stationary state means that the probability density of H does not change in time anymore. So dp/dt is 0. Then actually, it's easy to find that such a stationary solution is given by this. Probably it's a bit tricky to derive, but at least it's very easy to confirm that this is the solution. So you just insert it to here and note that, so all you need to show is that you take functional derivative, to this P, and if you take the functional derivative of this P and get new Laplacian H in front of P, then this term will cancel with this term. So dp/dt becomes 0. And it's easy to check that. So I recommend you to do that when you have time. So anyway, this is a stationary solution for the Edward-Wilkinson equation. And what it means? What does it mean physically? In fact, for the one-dimensional case, we can give a physical interpretation to this stationary solution. For one-dimensional case, this probability density is exactly the probability density for the simple Brownian motion. So the height h corresponding to the stationary solution here is just given by some coefficient times b of x. And this b of x is just the coordinate of some Brownian motion called the standard Brownian motion. The definition of the standard Brownian motion is that the distribution of this b of x is a Gaussian distribution, and the mean value is 0. And about the covariance, covariance is defined by this. You may know that in the Brownian motion, the mean square displacement is proportional to time t. So if you take this kind of covariance, if you take this kind of mean square displacement, it is proportional to delta t. And that is the defining property of the Brownian motion. And when we say the standard Brownian motion, the proportionality coefficient here is 1. So that is the definition of the standard Brownian motion, and it is denoted by b of x here. And then the stationary solution of the Edward-Wilkinson equation, 1D Edward-Wilkinson equation, is just b times square root of a, and this a comes from here, and this is d over 2 nu. But let me just give a more intuitive description. It means that the stationary interface we have in the Edward-Wilkinson equation, the stationary interface may look something like this. The vertical axis is h, and the horizontal axis is x. Then this fact means that this interface is actually equivalent to the trajectory of a Brownian particle. So now consider some Brownian particle, particle exhibiting Brownian motion, and it is one-dimensional Brownian motion, and the coordinate is b, okay? Now I plot the coordinate in the vertical axis, and the horizontal axis is time for that Brownian motion. And then the trajectory of the Brownian motion may look something like this. This fact that the stationary solution of the Edward-Wilkinson equation is equivalent to the Brownian motion guarantees that our stationary Edward-Wilkinson equation is equivalent to such a trajectory of one-dimensional Brownian motion. Okay? That is a very important property about the one-dimensional Edward-Wilkinson equation. And from this, actually, we can derive the exponent alpha for this case. As I said, a defining property of the Brownian motion is that the mean square displacement grows like delta t. But the time variable for the Brownian motion is, time variable for the Brownian motion is the space coordinate for the interface. So this
Excuse me.
mean square displacement, yes.
Very bottom part of your slide is kind of cut off.
Oh.
And I can't see the last equation.
That's right.
I guess you're showing something.
Yes, thank you for that. Okay, sorry for that. Yes, so the defining property of the Brownian motion is that mean square displacement grows like square root of time. Now, time for Brownian motion is the space coordinate for interface. So it means that, and then the coordinate of the Brownian motion is the height for the interface. It means that the mean square displacement of the height, so the squared of the change of height is proportional to delta t for Brownian motion, that is delta x for the interface. So for a given this change of the space coordinate delta x, we expect that the height change during the space translation over delta x is height change delta h for the space translation delta x is proportional to delta x square root of delta x. That is a consequence of this equivalence to the Brownian motion. And this 1/2 is exactly what the exponent alpha describes. So it means that alpha is 1/2. So yes, and of course it is consistent with the equation of alpha I showed in the previous slide. Okay, so that was for the Edward-Wilkinson equation. Now for the KPZ equation, we have this squared gradient term. So in the Fokker-Planck equation, we have squared gradient term here. Then what is its stationary solution? Unfortunately, stationary solution is not available for general dimension D. However, very luckily, for the one-dimensional case, we can show that the stationary solution of the Edward-Wilkinson equation turned out to be the stationary solution of the KPZ equation as well. In other words, this probability density for 1D, for one dimension, is the solution for the KPZ equation as well. And this is actually easy to show, because the only difference for the Edward-Wilkinson equation is this term. If we plug this solution to this square gradient term times p in this Fokker-Planck equation, and if that term gives 0, then it means that that is the solution of the KPZ equation as well. Do you understand? This term is the only addition in the KPZ equation version of the Fokker-Planck equation. So if this term vanishes, then the solution should be identical to the Edward-Wilkinson equation and the stationary solution of the Edward-Wilkinson equation. And that is easy to show for one-dimensional case. We just use partial integration and we can show that. Okay, so the mapping I described in the previous slide is actually also valid for the 1D KPZ equation. Such a trajectory of the Brownian motion is also equivalent to the stationary interface of the KPZ equation. And it immediately follows that alpha is 1/2 for the KPZ class as well for 1D. Okay. And since we already derived this scaling relation, alpha plus z is 2, we obtain this set of exponents. Alpha is 1/2, z is 3/2 because of this. And then beta is just the ratio of alpha to z, so it is 1/3. So we derive all exponents for the 1D KPZ class. Okay. Next, I'd like to quickly comment on the well-definedness of the KPZ equation. So KPZ equation looks like this. And I'd like to ask if this equation is well-defined or not. So I introduced this equation as if it is obvious that this makes sense, but actually it is not. It is a very strange equation. Why? That's because we have this noise term ether, and this is white Gaussian noise. The noise is uncorrelated. So even if you compare noise term at two very close positions, then the random variables are uncorrelated. So it can take very different values. So this is discontinuous in space everywhere. It is very pathologic term. Okay, but still, in physics, we often have this kind of thing, and usually it doesn't cause any serious problem. For example, this Laplacian term, so this apparently requires taking derivative in space, taking derivative to such discontinuous. Okay, so maybe I skipped too much. Since eta is discontinuous everywhere, and h grows with the influence of this eta, h itself is basically discontinuous everywhere. Oh, sorry, it's singular everywhere. It's non-differentiable everywhere, basically. So I showed that the stationary KPZ interface is equivalent to the trajectory of the Brownian motion, and that is non-differentiable. So mathematically speaking, this space derivative is something very weird, almost illegal. However, it doesn't cause a serious problem for the Laplacian term because, very roughly speaking, Laplacian h can take very large value, but it can be large in either positive, both positively or negatively. So as long as we want to know about the statistical properties like the mean, variance, and cumulants, then we take some kind of average on this. And since there are positive and negative values, those singularities are canceled each other, and we don't have a serious problem, at least from the physical point of view. However, this squared gradient term is different. This is squared, so it is always positive. We don't have such a cancellation of positive and negative numbers. So the combination of this white noise and this squared gradient term is really pathologic, and KP's equation as is actually ill-defined. This is a very bad news to you. I mean, I spent nearly more longer than 1.5 hours, and in the end, I'm saying that the KP's equation does not make any sense. However, so it is ill-defined. So it is not trivial what this equation means at all. I mean, it is ill-defined. It doesn't make sense. In particular, what is that solution? And so this is a very bad situation for us, but fortunately, there is an answer to circumvent this kind of problem. So at least for the one-dimensional case, which is established, we know how to answer this problem. So let me briefly sketch that. KP's equation looks like that. And let me take the Kohl-Hopf transformation, which is defined like this. So let me introduce this new variable z defined by exponential of h with some coefficient here. And suppose we can use the usual chain rule of derivatives, then we can transform this KP's equation to this kind of equation for z. dz dt is Laplacian z plus a coefficient z times either. We don't have this nonlinearity anymore. This nonlinearity is canceled by this Kohl-Hopf transformation. Wow. But so the equation might look simpler, but instead of the nonlinearity, we have this multiplicative noise term. I mean, we have this product between the variable z and the white Gaussian noise either. This kind of term is called multiplicative noise. And The definition of such multiplicative noise is very delicate. There are various definitions of the multiplicative noise term. If you are interested, you can refer to any textbook of stochastic processes like this one. And let me skip the explaining the definitions of the definitions, but just let me jump to the conclusion. There are two important definitions of the multiplicative noise. One is so-called Ito product, and the other is called Stratonovich product. And different definitions come from different ways to take the continuous limit. Let me skip that. And then from the body of knowledge on stochastic calculus, we know that the usual chain rule of derivatives is actually valid only for the Stratonovich product. It means that the differential equation we have here, by the way, it is often called the stochastic heat equation. This differential equation, if we want to get it from the KPZ equation, then we have to use the Stratonovich product for this multiplicative noise term. Then it is equivalent to the KPZ equation, but of course the KPZ equation is ill-defined, so the stochastic heat equation in the Stratonovich product is also ill-defined. The problem remains. However, we are basically stuck here, but then just let's try to consider Ito product version of the stochastic heat equation. Let's define the variable z by this equation. Now, and here, the multiplicative noise is defined with the Ito product now. For the Ito product, the chain rule cannot be used, or different versions of the chain rule must be used. So it cannot be mapped to the KPZ equation anymore. It is something different. But for this stochastic heat equation with the Ito product, in fact, we can show, I cannot show, but mathematicians can show that solution of Z is well defined. And this equation itself is well defined. It is well defined, even mathematically. Now, then let's use this as the starting point. KPZ is sick, so just put it in the garbage. And let's start with this stochastic heat equation with Ito product, which is well defined, and then just redefine, or not redefine, but let's define H by log of Z. Of course, this is inspired from this Kohl-Hopf transformation. Let's define H by using the solution Z of the stochastic heat equation. And this is what people call the solution of the KPZ equation. So this is how the ill-definedness of the KPZ equation is kind of compensated or solved in the literature. Okay. So this is the meaning of the KPZ equation. And in mathematics, there is a rich literature on this kind of stochastic processes. And there is another approach not related to the Kohl-Hopf transformation to define the solution of the KPZ equation. And Fields Medal was given to Martin Heiler for this achievement. Okay, so anyway, this is just a kind of side note about the well-definedness of the KPZ equation. If you are interested, you can get more information from those literatures. And just for practitioners, one note I can make is that interpretation of the KPZ equation is delicate. KPZ equation itself is ill-defined. So if you are used to simulation, you may think, okay, let's do simulations of the KPZ equation. You discretize your space and time, and you get something. Okay. Usually, by taking the continuous limit, so by taking your space interval, delta x, very small, then we expect that the solution of the simulation approaches to the real solution of the partial differential equation. However, that is not the case in the KPZ equation. KPZ equation is ill-defined, so you don't reach any limit. And the interface typically grows faster and faster as you approach the continuous limit. So that is one remark for fractionals. Okay, so that is what I wanted to say about the KPZ equation. And do you have any question? If not, since I spent already nearly 2 hours, I'm sorry for that. Let us take some short break here. 5 minutes are fine. I know it's a bit short, but I'm a bit behind the schedule. So let us resume at 5:03.
Okay.
Yeah. And in the meantime, I'm happy to take questions if you have.
Hi, Professor.
Yes, hi.
I mean, could you explain why that KPZ equation is ill-defined? Because I just lost track of your thoughts.
Okay. So it depends on what level of understanding you want to have. If you are happy to get an intuition, then the idea is described here. In a nutshell, in the KPZ equation, you have 2 terms that are contradictory to each other, kind of. So this eta is a white Gaussian noise. It is uncorrelated in space and time. So if you compare eta at position x and at another position x prime, then eta at x and eta at x prime are totally uncorrelated, even if x prime is very close to x. It means that eta is discontinuous in space. Yeah.
See, yeah, yes.
Yes. And you have such an eta in the time evolution equation. So H is also very singular at everywhere in space. You can see that in this real trajectory, real profile of the interface. It is very irregular.
I see.
Although it is continuous, it is not differentiable. You cannot take the derivative, spatial derivative in the mathematically rigorous sense.
Yeah, then why does this nonlinear term matter? Like why does this contribute to the ill-definedness?
Yeah, sure.
KPs?
Yeah. So first, let me say about the Laplacian term. So the problem of having such a very irregular structure is that if you are forced to take something like derivative, it diverges. In other words, okay, let's explain like this. Instead of having white Gaussian noise, let's introduce some correlation in space. Okay, so instead of delta correlation here, you consider some finite correlation in space, like let's say exponential minus x prime squared, something like this. If x and x prime are separated further, then the variance decreases, so correlation weakens. If 2 points are close enough, the correlation is stronger. That is the kind of the correlation I introduced. Okay. With that definition, eta is not. Sorry. Where am I? Yes. With that definition, eta is not discontinuous anymore. It is continuous.
Okay.
And then you can take derivative safely. And what you can show is that, so here, eta has a finite correlation length in space. Let's call that correlation length kappa, for example. Then if you take the limit of vanishing kappa, you can show that the typical amplitude of this Laplacian term goes to diverges. I mean, it becomes larger and larger as kappa becomes smaller. But it can be positive or negative, depending on the fluctuations you have. So as long as you are interested in the mean value, for example, if you take mean of that, then taking mean average of positive and negative values, those positive and negative values are canceled out, and actually you don't have a serious problem here.
Oh, I see.
You
So
understand what I
it's,
mean?
yeah, it's because, yeah, the nonlinear term is always positive. So the average.
Exactly.
always-
Such a cancel.
Yeah, so it
yeah.
diverges to infinity.
Yeah,
Okay,
yeah,
I see.
yeah. And you
See.
can show that rigorously, actually. So again, you introduce some correlation lengths in the noise, and then you yes. So you consider this stochastic heat equation with correlated noise. Okay. And then you define H by this transformation and try to take the mean of H. Then what you can show is that as kappa, the correlation length for eta becomes smaller, this mean H grows faster and faster. So in the limit of the vanishing kappa, so in the limit of the white Gaussian noise, this H grows infinitely fast. So this is the source of the problem. H grows infinitely fast, so this cannot be defined properly. So all the problem is in the absence of correlation of the noise term. And that is incompatible with the squared gradient term here. Is it
Okay,
fine?
I see.
Yeah?
Yes,
Yeah.
yes. Thank
Okay,
you.
great.
Thank you, Professor.
Okay, and I also got another question. Is there any difficulty when we use KPZ in the discretized simulation? It depends on how you define the difficulty. So of course, you can get something by simulations of discretized KPZ equation. But one remark is that you cannot take the continuous limit. If you change your discretization step, like delta x, very small, then your simulations become unstable. I mean, you don't reach any limit. that is one caution. So you have to fix some finite delta x and you get something. But one good thing is that you can still study the KPZ class by discretized KPZ equation. So for many practical purposes, it is fine. Yeah. But if you want to study how if you want to measure the coefficient, for example, I mean, if you want to measure the parameters that appear in the KPZ equation, like nu and d and so on, and then you need some special care. It may be, I mean, basically it is impossible to connect that to that of the original KPZ equation. So it is very delicate in that sense. And in the literature, there is a paper introducing some tricky way to do simulations of discretized KPZ equation, and that is the paper cited here. Here, that the authors introduced a special way to discretize the nonlinear term in order for the parameter values measured in the discretized KPZ equation become equivalent to those of the continuous KPZ equation. So if you are interested in simulation of the discretized KPZ equation, I recommend to read this paper. And then there's also a question about the Edward-Wilkinson stationary solution. Page 21. It seems that the probability density function is independent of H itself. So you mean it does depend on gradient H, but it does not depend on H itself. I guess this is what you mean. And can you directly prove this independence, or is it disappeared? Is it assumption? Okay, that's a great question. We can prove that, and that is the consequence of this height translation symmetry. So our solution must be invariant under this transformation. If P depends on the bare H, then it does not satisfy this requirement. So we must not have H itself in the probability density. So basically only derivative of H is allowed. Okay, great. And we are, so we ended the break time. So let's proceed with the chapter 3, and that is about the exact solution for the 1D KPZ class. Okay, let me give some overview. So from now on, I only talk about the one-dimensional case of the KPZ class. And as I gave a preview at the beginning, there has been tremendous progress on the understanding of the one-dimensional KPZ class, and that is because some exact solutions were found. And the first such progress was made in the year 2000. And since then, there are many exact solutions found, and it is still advancing pretty fast. So some models in the 1D KPZ class turned out to be exactly solvable. And in the year 2000, basically 2 models were solved, as written here. And then later, in the year 2010, the KPZ equation itself was solved exactly. So in this chapter, I'd like to describe main consequences of such advances based on the exact solution. So what we learned, what kind of physics we learned from this development? First thing is that exact solutions tell us very detailed statistical properties of the height fluctuation. So far, we only learned about the scaling properties, the exponents. However, thanks to the exact solutions, now we know the full distribution function of delta H. We also have some correlation functions for delta H, again, exactly. So far more detailed properties were now known. Second, it is not just some distribution and correlation functions were derived after very complicated mathematical calculations. Well, many people think that KPZ is too mathematical now and hard to get physics idea. It is true to some extent, but I would like to emphasize that actually there is a large room to understand the results of exact solutions intuitively from the physics viewpoint. As a matter of fact, I am experimentalist. I'm doing experiments. I'm not capable of following the mathematical proofs on the exact solutions here, unfortunately. But I do enjoy rich results and beautiful theoretical structure told by the exact solution. So this is what I want to tell. And also there is a set of non-trivial predictions as well. And the most important in my taste is predictions on what I call universality subclasses. So in fact, the distribution function and correlation functions are also universal to some extent. Different models show the same distribution function, same correlation function, so it is universal. But depending on the initial condition we choose, in fact, there are several classes of different universality, different distribution functions, several classes of different correlation functions. So in other words, the KPZ class defined by the scaling exponents seems to split into substructures, which I call subclasses. In this subclass, in one subclass is characterized by a corresponding distribution function and correlation function. In another subclass, it is characterized by another distribution and correlation function. This kind of substructure was shown exactly by such development of exact solutions. So let me explain those things. So to explain that, let me use model in the KPZ class. And this is one of the two models which were solved exactly for the first time, and that is the polynuclear growth model, often called PNG model. The definition of the PNG model is as follows. So we have a flat substrate, and suppose that we have random nucleation on the substrate, and the nucleation takes randomly in space. And when nucleation takes place, the height at that position of the nucleation increases by 1, okay? Initially it is flat, but if you have a nucleation at this point, for example, the height at this point increases by 1. Then you have step here, and that step expands at a constant speed. So this makes expanding plateau, okay? That is illustrated here. You have nucleation, and then the plateau made by this nucleation expands horizontally. And of course, there are other nucleations that can take place, and nucleation can also take place on top of the expanding plateau. And in this way, the interface tends to grow upward on average. Here, you have two expanding plateaus. So there are two steps approaching each other, and when steps meet each other, they annihilate and make a single plateau. Is the definition clear? Okay, and then by this definition, for this, without further constraint, we get the on average flat interface. Yes. So here I assume that my space is infinitely large. We have infinitely large space in X, and nucleation take place randomly, and then interface grows. As a result, interface grows upward. Okay. In the original model, it produces a flat interface. However, we can also describe a circular interface from this model. And to make a circular interface, we consider a situation like this. Instead of having an infinitely large substrate, we have a very narrow substrate, very tiny substrate, but that substrate expands laterally in time. Okay, substrate is expanding in time, and then nucleations take place only on top of that expanding substrate. This is what I wanted to express by this kind of illustration. You have an expanding table, and you have nucleations and resulting interface on top of that expanding substrate. Okay. So my interface is now bounded by the substrate. So it must be curved. Yeah. So in this way, we can make curved interface. And in fact, it is not difficult to show that the mean height profile is actually a semicircle. So we actually have a circular interface by this procedure. So let me recap. If I add a constraint that nucleations can only take place in this region, then I get the curved interface in this model. Okay. Now, let's describe this process in a space-time plot. Okay. What we have is this kind of process. And in the space-time plot, where the horizontal axis is X and the vertical axis is time, we get this kind of sketch. So here, black dots are nucleations. And when the nucleation takes place, I said that it produces it produces an expanding plateau. In other words, the two steps on both sides of the plateau are separating at some constant speed. That is expressed by this diagonal line. Okay. And when two steps meet each other, they annihilate. Okay. And for the circular interface, I said that we have this constraint. Nucleations occur only within this region. This corresponds to this diagonal axis. Okay. So nucleations take place only above those diagonals. Okay. This is the kind of the space-time plots we have. And of course, maybe this sketch is a bit misleading. There can be nucleations everywhere above these diagonals. So here too, there too, there are nucleations and the diagonal lines corresponding to the steps. Now, we are interested in the height at time t, and let's focus on the height at time t and position 0. This sketch, in this sketch, the solid lines correspond to the locations of the steps. When a step passes, the height increases by 1. It means that the height increases by 1 each time we cross this black solid line. So h is 0 here, 1 here, 2 here, 3 here. So if we want to know h at 0t, we need to count the number of lines to pass if we start from 0, 0 to 0t. Okay. In this case, we need to pass 1, 2, 3 lines. So h here is 3. Okay. And this is equivalent to the maximum number of dots passed by this dashed line, which is called the directed polymer. And this dashed line is this is a segment, and the two ends of this segment are fixed at position 0, 0 and 0t. Okay, this dashed line, two endpoints are fixed at 0, 0 and 0t. And this segment has a constraint that the direction of the segment must be always between 45 degrees to 135 degrees. So it's forbidden to make this kind of U-turn. It always needs to go upward. That's why it is called directed polymer. Okay. And then the problem we have is that we would like to let this polymer to pass as many black points as possible. In this example, this polymer can pass at maximum 3 black dots, but it cannot pass 4 black dots. In order to take 4 black dots, it needs to take a forbidden direction like this. It is, it is not between 45 and 135 degrees. Yeah. So h is equal to the maximum number of black dots passed by such a directed polymer. And this is often called the point-to-point problem of the directed polymer. Now, oh, by the way, this mapping is a bit complicated. So if you feel you get lost, of course you can ask questions. But if you give up, just try to take the final message, and it's okay if you don't understand the derivation. Okay, anyway, h is mapped to this kind of problem. And then let's describe the positions of the nucleation points by coordinates along the two diagonal axes. And this coordinate is just the index along this axis. For example, this nucleation point has the smallest value of our coordinate, so coordinate 1 is given. This nucleation point is the second smallest, so coordinate 2 is given, and so on. It is just the index. It is just the order of appearance. And we do the same thing for s-axis. And then we just write down the coordinates r and s for all the nucleation points we have. Okay. In this example, for this nucleation point, the coordinate is 1, 4. Okay, 1, 4. For this nucleation point, the coordinate is 2, 7, 2, 7, and so on. I just make listed all the coordinates. And then we realize that this is a permutation. Yeah. In the first row, we have just 1, 2, 3, 4, 5, and up to 8. In the second row, we have a permutation of that. And this permutation is random. Then the quantity of interest here, the maximum number of dots passed by the directed polymer, is actually the length of the longest increasing subsequence of this random permutation. In this example, increasing subsequence So for example, we see 478. Yeah, it is an increasing subsequence, 478. Its length is 3. And that is the height here. We also have 236. The length is 3. However, we cannot find increasing subsequence of length 4 or longer. Yeah. So our H is now described in a purely mathematical term. It is just the length of the longest increasing subsequence in random permutations whose length is given by Poisson distribution. And then it is now pure mathematics, combinatorics, and there are techniques. So there are a lot of developments in this combinatorics before the year 2000, and that helped mathematicians to solve this problem finally. And this is the final result. Value of H is given by this quantity, this equation. The first term is 2 square root of S, and S is the area of this rectangular region, this diamond region. So it is simply expressed, this is T squared divided by 2. The second term is S to the 1/6 times some random variable denoted by chi GUE. And in terms of time, we get this. The first term is a deterministic term, and it grows like time. Okay. For the interface, H grows linearly with time, basically. But this term does not have fluctuations. The second term has a random variable here, so it is a fluctuating term, and the amplitude grows like T to the 1/3. And this 1/3 is a beta exponent of the 1D KPZ class. So at least we confirm the KPZ exponent. Now, this random number, chi GUE, the property of this random number was derived by this kind of derivation. And this is a random variable of a distribution defined previously in random matrix theory, and that is called the GUE Tracy-Widom distribution. So what is the GUE Tracy-Widom distribution? Tracy-Widom distribution is a distribution of the largest eigenvalue of certain class of random matrices, and that is Gaussian random matrices. And we would like to explain particularly the case of the GUE random matrices. So the GUE random matrices, GUE is short for Gaussian unitary ensemble, and it is one of the most famous kinds of random matrices, which is defined as follows. In this ensemble, we consider large complex Hermitian matrix, n by n, and each matrix element is drawn independently from Gaussian distributions. And since it's Hermitian, the diagonal components are real numbers, and each component is drawn from independent Gaussian distribution with mean 0 and variance n. For non-diagonal terms, off-diagonal terms, since the matrix is a complex Hermitian matrix, it has real part and imaginary part, and both of them are drawn from independent Gaussian distributions with mean 0 and variance half n. Okay. And then we want to know the eigenvalues of this matrix. N by n Hermitian matrix has n real eigenvalues, and we can consider the distribution of such eigenvalues. And it is known that the distribution of all such eigenvalues is given by a semicircle function spanning from -2n to 2n. And then we focus on the largest of the n eigenvalues. Okay, we have n eigenvalues and we just focus on the largest one. That largest eigenvalue is necessarily close to the rightmost edge of this distribution. So it's basically 2n. But mathematically, we can show that it is more precisely described as follows. It is basically 2n, but as a subleading term, we have the subleading term is proportional to n to the 1/3, and it is stochastic. So we can define a random number chi-GUE by this normalization, and the distribution of this chi-GUE is called the GUE Tracy-Widom distribution. So again, this is a distribution of the largest eigenvalue of random matrices, GUE random matrices. So I explained the case of the GUE Gaussian unitary ensemble, so the case of the complex Hermitian matrices, but we can define Tracy-Widom distribution similarly as the largest eigenvalue distribution for real symmetric matrices, for example, and that is the case of the GOE Tracy-Widom distribution. We can do similar thing for Cartesian self-dual matrices, and that is the case of the Gaussian symplectic ensemble, GSE. And those distributions may look similar to the Gaussian distribution, but there are many fundamentally different points. For example, this is asymmetric. This is off-centered. The mean is not 0, but it is off-centered and it is asymmetric. The right tail is decays like exponential minus constant times chi to the 3/2. The left tail decays much faster. It is exponential to the minus chi cubed. So this is such a particular kind of distribution, and the analytic expression for the Tracy-Widom distribution was derived in random matrix theory. And that distribution, that particular distribution, which has nothing to do with interfaces, was found by this derivation. Okay, and well, for those who want to know the definition, well, I already explained the definition, but for those who want to draw or deal with the GUE Tracy-Widom distribution, analytic expression is known, and it is expressed in terms of certain determinant called the Fredholm determinant, which is an extension determinant for functional space. And there is also another definition based on the Pan-Louvet 2 equation, which is a famous equation for integrable systems. Anyway, let me skip details. And for the users of the Tracy-Widom distribution, if you go to the web page by Prehofer and Spohn, you can obtain a numerical table of the distribution function. And also, if you use Mathematica, recent versions of Mathematica have a built-in function for the Tracy-Widom distribution. So you can draw this kind of thing immediately on Mathematica. Okay. Now, so anyway, for the PNG model, if we consider circular interfaces, we get the GUE Tracy-Widom distribution as the distribution function for the height variable h. Now, what happens for the flat interfaces? The difference between the flat and circular interfaces is that for the circular interfaces, we considered constraint on the locations of the nucleations. Nucleations were restricted to this region. And that's why we considered this, we had this kind of light cone. However, for the flat interfaces, we don't need this constraint. nucleations occur everywhere in space. But if we want to consider the point 0t, then it is only the region here that can affect the height at this point. Yeah. In our problem, the propagation of the step is a kind of light. It is a propagation, fastest propagation of information. So all the events that can affect this point are limited below those diagonals. So for the flat interfaces, we consider such a triangle instead of the rectangle. And then the problem is equivalent, except that. So we have a directed polymer. Now the bottom end point of the directed polymer can freely move on this line. So it is a line to point problem. And then we need to count the number of maximum number of dots passed by such a directed polymer. To solve that, we consider a mirror image. And then the problem apparently reduces to the square here. But of course, the difference is that this is a mirror image. So the locations of the nucleations are just the ones reflected from the top part of the rectangle square. So in other words, we have additional time reversal symmetry for the flat interfaces, and that addition of the symmetry changes the limiting distribution from GUE to GOE, Tracy-Widom distribution. So again, the Tracy-Widom distribution arises for flat interfaces, but the point is that the symmetry is different between those two problems, and we find another distribution function, which is interestingly that for the GOE random matrices, so that for real symmetric matrices instead of the complex Hermitian ones. Okay. And then let me skip to detail, but it is known that yet another distribution can be derived for the stationary interface. Suppose we have interface. So now we consider a stationary interface. So it's something like this, and it is equivalent to the Brownian motion. We compare the interface at time t0, sometime t0, and another time t0 plus t. And then we ask how much this interface grows during this time t. Okay, we consider the height difference between time t0 and t0 plus t. And then, in fact, we can make a similar argument based on the space-time plot. And let me skip all the details. But the conclusion is that it turned out that a distribution called the bike lanes distribution describes the fluctuations of the height in the stationary KPZ interfaces. Okay, so yes, and there is a definition of the bike lanes distribution based on the Pan-Lebedev equation, and unfortunately, or I don't know, there is no link to random matrix about this distribution. Anyway, the main point is summarized in this slide. It turned out that the single KPZ class, the 1D KPZ class, splits into several cases depending on the shape of the interface or the situation we consider. The first case is that for the circular interfaces, and the distribution function is given by the GUE Tracy-Widom distribution. The second case is the flat interface, and the distribution is given by the GOE Tracy-Widom distribution. The third case is the stationary case. It is about the growth of stationary interfaces. And then the distribution is the bike lanes. And those are universal. I mean, it doesn't depend on systems or, even including experimental systems. We find that distribution universally as long as we have similar kind of shapes, global shapes. And all these cases share the same scaling exponents. So in the usual definition of the universality class, those are in the same universality class, and that is the 1D KPZ class. But it has such an internal substructure. And although I have to skip, there are also exact solutions for the correlation function, at least for the equal time case. And that is given by what is called early 1 process for the flat case and early 2 process for the circular case. It's just a name, sorry. And 2-point correlation between 0.00 and xt is also derived for the stationary case, and that is derived by Prefoffa and Spon, and it is often denoted by GKPZ. And this is a function denoted by GKPZ. Anyway, so those things were derived exactly. And as I said, they are universal, and I tested that experimentally. I mean, in my group, we tested that experimentally, and all these distribution functions were found in the liquid crystal turbulence. All right, and I'm afraid I have to skip things. So I'd like to go to the quantum part, but for that, I'd like to explain a bit about this model. So let me do that. Now I'd like to explain another model in the KPZ class, and that is the asymmetric simple exclusion process. This is a model of stochastic particle transport. Okay, so you have a lattice, and each side is either empty or occupied, okay? And those particles can hop to neighbors stochastically, and they hop according to the hopping rate P and Q. It hops to the right neighbor by the rate Q, at the rate Q, and it hops to the left neighbor at the rate P. And P and Q are taken asymmetrically. For example, Q is greater than P, so it has higher chance to hop rightward. So particles move stochastically, but on average, they flow rightward, okay? And the only interaction between the particles is the volume exclusion. So if there is already a particle here, then this particle cannot hop rightward because it is already occupied. So that is the only interaction. So this is a simple model, but it is very non-trivial and it is very rich. It is actually an integrable model. If you are interested, I recommend those reviews. And thanks to the integrability, many properties can be obtained exactly. And also, it can be mapped to interface growth model. For the mapping is as follows. An occupied side corresponds to the downward slope, and the empty side corresponds to the upward slope. And then this configuration corresponds to this kind of interface profile. And if this particle hops to the right, initially it is occupied and empty, so it is downward and upward. But if this particle hops to here, it becomes empty occupied, so it becomes upward, downward. So this part of the interface grows by 1 unit. So this is interface growth model. Particles tend to flow rightward, so the interface tends to grow upward, and this is interface growth model, and this is in the KPZ class. And then many properties are solved exactly for this model as well. Since the year 2000, about the distribution properties. And all the three universality subclasses I described in the previous slide were obtained as well, at least for the simple case of the A set. And the circular case corresponds to the step initial condition. So in this initial condition, all sides in the left half are occupied, and all sides in the right half are empty. This corresponds to this kind of V-shaped interface, and then a curved interface is obtained. The flat case corresponds to this kind of alternating initial condition. You have empty, occupied, and so on. And this corresponds to this kind of zigzag initial condition, but it is on average flat. And we get the property of the flat interfaces, like the GOE trace-evident distribution. There is a solution for the stationary case as well. The stationary measure of this model has been known since a long time, and the bike length distribution can be shown. So anyway, the point is that those universality subclasses correspond to those initial conditions. Okay.
Hi,
Yes.
there's a question on Slido, and I just put it on chat.
Okay. Somehow.
Right. Shall I?
Yeah. Okay.
Oh yeah, that one.
I see. Okay. Sorry. Yes. Where does the entirety of GUE arise in the PNG problem? Does it correspond to some symmetry of the model? Yeah. These are difficult kind of question. So all I can tell, I mean, one thing I can tell is that, in fact, the PNG model does not directly correspond to a random matrix problem. For a finite time, it really doesn't correspond to a random matrix. But only in the limit of the infinite time, it goes to the same limit as the infinite n limit of the random matrix. So there is no direct correspondence between the PNG model and the random matrix. Only the limit is the same somehow. This is one remark. And another remark is that, nevertheless, symmetry matters. As I explained here, the difference between the circular and flat interfaces are the absence or presence of the time reversal symmetry. If you don't have time reversal symmetry, you have GUE trace-evident distribution. If you have the time reversal symmetry, you have the GOE trace-evident distribution. And in fact, that is analogous to another example of physical problems related to random matrices. And that is nuclear energy level statistics. If you consider the distribution of the energy levels on the nucleus, it's known that the spacing between neighboring energy levels is can be described by the difference between neighboring eigenvalues of random matrices. And it is known that if there's no time if there is time reversal symmetry, then we have statistics of GOE random matrices. But if you don't have time reversal symmetry, for example, if you have magnetic field, then you don't have time reversal symmetry and you get GUE statistics. So somehow GUE is often observed in the case without time reversal symmetry, and GOE is observed under the time reversal symmetry. And for some reason, it is the same here. So symmetry is relevant, but the trick here, I mean, why it is GUE and GOE are related in that way in this particular problem, I'm sorry, I cannot describe. So please refer to the paper cited here. This is physics paper, so there is no answer, but so please refer to a mathematical paper cited here or ask specialists. I'm sorry. Okay. Then okay, maybe probably I have to skip the part on the KPZ equation. So just let me say one word. Our KPZ equation can be mapped to many different problems. I already explained that by Kohl-Hopf transformation, it's kind of mapped to the stochastic heat equation. Precisely speaking, the stochastic heat equation is the real definition of the KPZ equation. Then, in fact, we can describe this in terms of path integrals, and Z can be described by something like this. So, in a sense, this is something like Schrödinger equation. Of course, time is imaginary here, but it looks like Schrödinger equation. This is a Laplacian term, and you have potential ether. Z corresponds to the wave function. Yeah. And then you know that the Schrödinger equation in quantum mechanics can be expressed in terms of path integral. We can do the same thing here. Z can be expressed by path integral, and then the integral looks like this, and it can be interpreted as the partition function. Yeah, it looks like summation of exponential, and the potential of this partition function has some energy that corresponds to the elastic energy and the random potential. And so it is the energy for polymer, actually, expressed by x of tau, xt. And this polymer has the elastic energy, and it is placed under random potential minus ether. And then if you compute the partition function, you get this Z. So the KPZ equation is equivalent to this kind of directed polymer problem. Again, directed polymer, but in continuous version. And then if we write down instead of Z itself, we can write down the nth order moment of this Z. So we define this psi. And in fact, after some calculation, not difficult, even I can follow, this psi is shown to follow this equation, which again looks like a Schrödinger equation. Time derivative of this psi grows like this with this kind of Hamiltonian, and this Hamiltonian is defined by this. And this is the Hamiltonian known in the literature of quantum integrable models, and that is called the Lieb-Liniger model. This is one of the most important models of quantum integrability. So KPZ equation is equivalent to the Lieb-Liniger model. More precisely, the attractive version of that. The sign of the potential is minus here. And this is integrable model, quantum integrable model. So techniques in the quantum integrability, such as the Bed ansatz, can be used to solve the problem. And the Tracy-Widom distribution can be derived. Okay, so well, this is my bad. Okay, so let me stop about the KPZ. Let me stop chapter 3 here. I'm sorry for that. And let me quickly go the chapter 4, KPZ in quantum spin chain. Now the context is totally different. The question we want to ask is effective descriptions of spin transports in some quantum many-body systems. We want to know macroscopic descriptions of quantum systems. For example, we want to know how do macroscopic fluctuations in quantum systems, like quantum spins, propagate in space and time. And of course, there are many studies on that. And basically, fluctuations propagate in a diffusive way in many systems. But interesting exception is a class of integrable systems. So you know that integrable systems may have very anomalous propagation properties. So fluctuations may propagate ballistically instead of diffusively. And there is a framework of hydrodynamics for integrable systems called the generalized hydrodynamics, which was formulated by Benjamin Doyon and co-workers. So we have a theoretical framework for even for integrable systems, but the fate of this framework is delicate in the presence of symmetries. And that is the case that we want to discuss here. So what I wanted to tell is that there is no reliable solid framework to describe fluctuations of integrable systems under the presence of symmetry. And one particular model I want to describe in this chapter is the Heisenberg's model. You know, this is the model for magnet, and this is a textbook model. Yeah, the Hamiltonian is given by this spin operators, and here I have an anisotropy parameter delta. If delta is 1, this is anisotropic case. Sorry, if delta is 1, this is the isotropic case. And it is called XXX model. But if delta is not 1, it corresponds to an anisotropic case. And the question we want to ask is how spins propagate in this model. And it is known that the propagation is ballistic if delta is smaller than 1, but it is diffusive if delta is larger than 1. So the isotropic case, delta 1, is kind of critical point. And we have something special. And in fact, this isotropic case, the most basic case of the Heisenberg model, is recently discussed in the context of the KPZ class. So what people found numerically, for example, is that if you measure how the distribution propagates, how the profile propagates. So I shouldn't skip too much. So as the initial condition, we consider so-called domain wall initial condition. The left half is occupied by up spins, and the right half is occupied by down spins. Okay, initially it's all up in the left half and all downs in the right half. Okay, and then in the course of the time evolution, of course, some spins flip, some up spins may flip to the right, some down flips go to the left instead. So the interface here becomes broad in the course of time. And the way the interface is smoothened is the width of this interface enlarges as t to the 2-thirds for the isotropic case. And this 2-thirds is argued to be the dynamic exponent of the KPZ class. I mean, this exponent z is 3/2 for the 1D KPZ class, and that is what we have. So in the KPZ class, the correlation length grows like t to the 2-thirds, and we may argue that we see something that corresponds to the KPZ dynamic exponent here. And this is, numerically speaking, this is clearly seen by simulation. So this is the profile of the mean spin. This is the mean spin profile for 3 different times. And this is scaled perfectly if you scale your coordinate j by t to the 2/3. Okay. But if this is only about the exponent, then we can say it is probably just a coincidence. 2/3 is not a special kind of value. However, in the year 2019, it was shown that, again numerically, it was shown that even the 2-point function of this spin variable, spin at time 0 and position 0, and spin at time t and position j, that correlation function agrees quantitatively with the exact solution of the 2-point function for the KPZ stationary subclass. This is the plot. So with that, people are convinced that this is something not explained by just a coincidence. It's not only just 2/3. It's not only just an exponent, but this is a full functional form of the correlation function. So it must be something there. That is the beginning of the story. And Yamagichi-san, can I use 10 minutes or if it's difficult?
You can.
I can?
It's just, yeah, last lecture.
Sorry. Yeah. Okay, let me give 10 more minutes. I'm sorry for that. Okay, so this is the situation for the Heisenberg spin chain. Situation from numerical simulation. And it was the year 2019 about this 2-point function. And then after that, there are a couple of great experiments studying this possible relation to KPZ in Heisenberg model. One is a neutron scattering experiment. And this is in this paper in Nature Physics, published last year. Those authors studied the dynamic structure factor of spins of this particular magnet. And the specialty of this magnet is that it has this kind of configuration of wave functions. And thanks to this particular way of overlapping of wave functions, it is equivalent, it is very close to, it can be regarded rather precisely as the one-dimensional Heisenberg model along this line. Yeah, wave function is overlapped basically along this line only, and this is isotropic in this line. And neutron scattering is a useful method to study the dynamic structure factor. And in fact, in the KPZ class, the way the dynamic structure factor should look like in the stationary state was already computed by Prafova and Spon, by exact solutions. And if we take the low energy limit, then this structure factor should depend on q to the -3/2, and this is related to the KPZ exponent. So this is what experimentalists try to measure by this neutron scattering. And also one thing I skipped is that this correspondence to the KPZ class is argued to be valid for the infinite temperature case. At the infinite temperature, the stationary state is just a random distribution of up and down spins. And in that infinite temperature case, the correspondence, agreement with the 2-point function, the KPZ, was observed numerically. So experimentally, we should compare the case with high temperatures. So those experimentalists studied the dependence on the temperature. And for the highest temperature they used, the exponent was 1.35, which is a bit lower than 1/3. 3/2, 1.5. But for bit lower temperature, it is closer to 1.5. And those authors also compared with numerical simulations. They did exact numerical simulations using matrix product state. And the experimental data seem to match rather well with the direct numerical simulations. And with simulations, they can approach the lowest energy limit. Experimentally, this limit is inaccessible for technical reasons, but numerically they can do. And by approaching the vanishing omega limit, the exponent we see in the dynamic structure factor indeed approaches to 1.5 for the infinite temperature case. And for 300 Kelvin, we still see 1.5 in the lowest energy limit, but experimentally we cannot reach this limit. So it is argued that the experimentally accessible energy is somewhere around here, and that is smaller than 1.5, and this is what we see here. And numerically, the agreement with the exact solution for the dynamic structure factor was also confirmed. So the message is that although experiments cannot reach the lowest energy limit, they do agree with the results of the direct numerical simulation, and those direct numerical simulations do agree with the KPZ dynamic exponent, as well as the exact solution for the structure factor. So from this, by combining with such numerics, we can, well, I was kind of convinced that this material indeed seems to show fluctuations described by this KPZ class. And then the second experiment was totally different kind of experiment, and it was a quantum gas microscopy experiment, and it was published this year in Science. This is a cold atom experiment, and cold atom, these atoms were trapped in an optical lattice, and the atom we have here are either in this hyperfine structure state or this state. So in the nutshell, there are only two possible states for this atom in our systems. And we just denote the first state by up spin and the second state by down spin. And then for the particular parameters they chose, in fact, that the evolution of this system of cold atoms can be shown to be equivalent. Oh, sorry. Well, before that, the time evolution of this kind of cold atoms is given by the two species Bose-Hubbard model, which reads like this. And then for the particular set of the parameters they used for this experiment, this model can be shown to be equivalent to the Heisenberg model. So by observing how those cold atoms evolve in space and time, we can effectively do simulations of the Heisenberg Hamiltonian. And this is what they did. And they can observe the states of the atoms at a given time and space, although it is a destructive measurement. So if we start from a domain wall initial condition, I mean, if so we start from the initial condition is totally up spins in the left half and the down spins in the right half. And okay, so right down spin is bright here and up spin is dark here. And if we start from this initial condition, after some time, the system looks like this. Okay. And then to make a correspondence to the KPZ problem, in fact, ASAP is very useful. So I remind you that ASAP is one model in the KPZ class, and the mapping is that up spin corresponds to the occupied state of ASAP, and it corresponds to the downward height interface. The downspin, sorry, the downspin mark is somehow does not appear. Downspin corresponds to the upward slope, and this corresponds to the empty side of ASAP. And then the evolution of spins can be mapped to the interface problem. And this is what is suggested from simulations here. This agreement with the 2-point function of the KPZ suggests that, so actually what I draw here is a 2-point function for the gradient of H. So this suggests that the spin variable corresponds to the gradient of H. So that's why we considered this kind of mapping. Upward spin corresponds to the gradient, minus gradient of how to say, negative gradient of height. Downspin corresponds to the upward gradient of height. And then the bare height can be obtained by integration. More precisely, this corresponds to the number of spins that passed the boundary x0 from left to right. So you just count the number of up spins that crossed this origin x equals 0 from time 0 to time t, and that is the height. And they measured experimentally how this height, or they use p, growing time, and the fluctuation amplitude. So the standard deviation grows like t to the beta, with beta close to 1/3. And this is the one-dimensional KPZ exponent. The mean height grows like t to the 2/3. And in fact, this is something different from the usual KPZ class. In the usual KPZ class, the mean height grows like t. But in this Heisenberg model, mean height seems to grow like t to the 2/3. So there is a difference. But if we focus on the fluctuation, we do see the exponent of the 1D KPZ class. And they also measure the distribution of this P. And their conclusion is that they see the Tracy-Widom distribution, which is characteristic of the KPZ class. However, the values of the, so they measure the quantifier of the distribution called the skewness. And the value of the skewness they found is closer to the GOE Tracy-Widom distribution than GUE Tracy-Widom distribution. And since we started from the domain wall initial condition like this, that corresponds to the this case, the step initial condition for the ASAP. So actually this corresponds to the circular subclass for which we expect the GUE Tracy-Widom distribution. However, the experiment on the Heisenberg model, I mean, quantum gas microscopy experiment showed the GOE Tracy-Widom distribution that is characteristic of the flat interface. So some details, if I can say, are different, but in any case, in this paper list, they emphasize that they found the Tracy-Widom distribution. So this is regarded as another piece of evidence of agreement with the KPZ class. So I'm approaching the end of the story. I'm almost there. So this is the summary of what I wanted to tell about the isotropic Heisenberg model and the KPZ class. Exponents seem to be the same. The stationary 2-point correlation is found, agreement is found about the 2-point correlation. And that agreement is with the exact solution for the stationary KPZ class. 1-point distribution was measured by quantum gas microscopy experiment and the trace rhythm distribution seems to be there. So this is a kind of agreement. However, as I already said, the type of the trace rhythm distribution seems to be different between the isotropic Heisenberg and the standard KPZ. More seriously, the way the mean height grows seems to be different. And that difference comes from the way the mean spin profile is scaled. As I told, the mean spin profile of the Heisenberg model scales like t to the 2/3. And this is anomalous diffusion. And it is discussed to be because of the dynamic exponent of the KPZ class. However, in the KPZ class, if we measure something similar, for example, in the ASEP, the particle density corresponds to the spin variable. And if we take the mean profile of the density, in fact, it doesn't scale like this, but it scales simply like x to the x divided by t. So in fact, the way the mean profile is scaled is different between the isotropic Heisenberg and standard KPZ. And one last thing is that the stationary one-point distribution also seems to be different. And first of all, in the Heisenberg model, we have up-down symmetry. Yeah, up spins and down spins are equivalent. However, if they are equivalent, then the interface don't grow. Yes. If up spins and down spins are equivalent, it means that down slope and up slopes are equivalent, and particles just have so interfaces would have up-down symmetries, so they don't grow preferentially upward. So in fact, the fundamental difference exists in the symmetry. So the symmetry seems to be different between the two cases. And this results in the difference in the distribution function between the two cases. So there are such dissimilarities between the two cases, and those dissimilarities are often not emphasized in the literature, but they do exist. So we have to be a bit careful about that. So I have to say that I don't think KPZ is unrelated to Heisenberg spin chain. I don't think this agreement with the exact two-point function found in the isotropic Heisenberg is just a coincidence. I do believe KPZ is related, but we definitely need to understand how such disentanglements, how such disagreements, apparent disagreements need to be understood. So there are similarities and also dissimilarities. Important thing is that we need to disentangle them. So we need a theory, real theory, to describe or account for those observations. And that is a particular open problem, I would say, in this context. And there is no solution obtained yet. So as a final remark, I started this lecture with a reference to the equilibrium critical phenomena, physics of critical phenomena, and I compared the histories of equilibrium critical phenomena and that of the KPZ equation or KPZ class, and I said they may look similar in the sense that KPZ has exact solutions. Well, first of all, it is about the universal scaling laws and the universality class. There are exact solutions, there are experiments, and there are many deep things there. However, if I compare with the equilibrium case, probably we are here, but this just corresponds to somewhere in the mid-20th century. So we had exact solution at that time. We had several experimental observations, showed the universality, but at that time, we didn't have clear-cut theory like the renormalization group theory. So indeed, there are many things that we don't fully yet understand, especially about the correspondence, mysterious correspondence to the Heisenberg model. So as a final remark, let me say that, so we can ask, I mean, I'm very curious if we can expect, so I believe we are still there. So I'm curious if we will see as glorious development as the Wilson's renormalization group and conformal field theory and so on for such scaling laws of the non-equilibrium systems. And of course, this is something particularly a very difficult and challenging problem. Probably we need decades. So probably we need power of young students and and young researchers. So why don't you try to make such a breakthrough if you are interested? And I would be very glad if you are interested in this kind of problem and get into interest from my lecture. Okay, I'm sorry for the extension, and I'm sorry also that I went very quickly in the second half, but I hope you enjoyed to some extent. Okay, thank you very much, and probably I can take a few questions if I can. In any case, thank you very much.
Thank you very much for a really comprehensive lecture. And so if there's some short questions, maybe.
Okay, one question. Is quantum effect in the spin model? Sorry, is quantum effect in the spin chain important even in the infinite temperature? I don't know. Probably I'm going to tell something wrong, but myself, I don't think it is necessarily restricted to the infinite temperature case. I mentioned the infinite temperature case because the first finding of the correspondence to the KPZ was done for the stationary case. And the stationary case for the KPZ equation, 1D KPZ class, is Brownian motion. And Brownian motion is a random mix of upslope and downslope. So that corresponds to the random mixture of up spins and down spins. And that's why it corresponds to the infinite temperature case. So to me, infinite temperature was just necessary to study the stationary state of the KPZ class precisely. However, we don't have such correspondence for this experiment, for example. Here, they started from a domain wall initial condition, and they just let spins evolve. So if I understand correctly, there is no correspondence to infinite temperature case here. And but still, we do see at least partial agreement with the KPZ class. So so myself, I think the correspondence to KPZ can be broader than just the infinite temperature case. And if that's true, then there may be some role of quantum effects, but I'm not sure. And I think no one has an answer on that. Okay. And
so maybe
yes.
Before you go to the next question, maybe we first close this session, and
okay, yeah.
If somebody wants to leave here, Then they can
Okay.
live here. Okay, so let me first close this session.
Yes.
So
Yeah.
thank you.
Thank you very
Thank you
much.
again for
And
this time.
I will be in the get together after this lecture. So
Yes.
probably I can answer to the remaining questions in that get together if you are there. Anyway, please feel free to talk to me in the get together.
Okay. I mean, staying here is just fine, but I'm just closing
Okay, yeah, sure.
because yeah, it sounds like it's gonna be
Yeah,
it's gonna
sorry.
take a bit longer. So
Yeah.
so thank you to
Thank
the
you.
audience for active discussion, and we'd really appreciate if you take your time to answer the questionnaire on the chat box.
Okay, great. So
And
can I continue
yes.
now? Can I
Yes, please. So
resume?
just
Okay.
yes.
Okay, great. The next question is integrability important for the model to exhibit the KPZ scaling? Can we observe KPZ scaling in non-integrable systems? Yes, that's a great question. Yes. So the answer is yes. So what we believe, I mean, what people working on KPZ believe is that the statistical properties of the KPZ class are universal in the KPZ class. Tracy-Widom distribution, GUE Tracy-Widom distribution should be observed in the circular case of the KPZ class, irrespective of the integrability. Both integrable systems and non-integrable systems should show the same statistical behavior. This is what we believe, okay? However, to derive the Tracy-Widom distribution, integrability is very useful. By using the special properties of the integrability, mathematicians can derive the GUE Tracy-Widom distribution for the particular models they consider. And then we believe that this is universally shared by all members of the KPZ class, irrespective of the integrability. And of course, this kind of claim is hard to prove mathematically, but some people are trying that. And also, from the experimental viewpoint, I did observe the Tracy-Widom distribution experimentally in the liquid crystal turbulence. I really don't believe that my experimental system happens to be an integrable system. You know, integrable systems are really rare, special kind of systems. I don't think let me say dirty liquid crystal turbulence system happens to be integrable. So to me, it is already convincing. I mean, my experimental results are convincing that the Tracy-Widom distribution and all other properties of the all other outcomes of the exact solutions of the KPZ class are observed also in non-integrable systems. Okay. Next. Is there any intuition about why infinite temperature is important? And that is I think I partially answered when I answered the first question in the Q&A session. So we consider the infinite temperature. My understanding is that we consider the infinite temperature because we want to make correspondence to the stationary state of the 1D KPZ class. That is equivalent to the Brownian motion. Brownian motion is a random mixture of up and down slope. Yeah. So in terms of spins, it is random uncorrelated mixture of up spins and down spins, and that is the stationary state of the infinite temperature Heisenberg model. So to me, this infinite temperature is only necessary to make the correspondence to the stationary state, but this is not directly related to the correspondence to the KPZ class. However, I don't think either, and people don't believe that KPZ is relevant for low temperature Heisenberg models. For ground state properties. And that is because, well, first of all, there is no satisfactory theory yet showing explaining the correspondence between the Heisenberg model and the KPZ class. However, one theory, so of course people are trying that and many people are studying that. And one interesting theory was proposed by Vir Burchandani 2 years ago in this paper. And he proposed that the KPZ might be a result of the KPZ might be derived by considering the pseudo vacuum of the Heisenberg model. So, in the ground state of the Heisenberg model is that all spins are up or down or in any direction. So suppose most spins are up, but only one spin is down, and then this is a quasi-particle, and this is spinon and quasi-particle. So we can describe the system in terms of quasi-particles and pseudo-vacuum that corresponds to the up spin state in this example. And then the time evolution of the pseudo-vacuum, in other words, it is a coarse-grained magnetization field, then it is given by Landau-Lifshitz model like this. And then phenomenologically, starting from this Landau-Lifshitz model, in fact, he showed, he eventually arrived at the noisy Vargas equation, which is equivalent to the KPZ equation as I described. So he considered the energy and the torsion as the two important conserved quantities describing this equation. And the energy is actually irrelevant in the renormalization group sense. So it's taken to be 0. And then the equation for the torsion is written down, and it looks like the noisy Vargas equation. And the source of noise is actually quasi-particles. So what we have in this system is not only the pseudo vacuum, but we have quasi-particles somewhere, and they are fluctuating, and they are considered to be source of the noise term in the coarse-grained description. So many parts of the theory are phenomenological, but if we accept all those things, then we get noisy Vargas equation, which is the KPZ class. So to me, this is another kind of support that the correspondence to the KPZ is not necessarily restricted to the infinite temperature case. What we need is probably pseudo vacuum and quasi particles, and I don't know how to say. So the situation considered in this phenomenological theory may be more essential about this mapping, but sorry, I cannot describe. And anyway, this is not a first principle kind of theory. So it is not a goal of the story, and it does not answer dissimilarities I mentioned between the usual KPZ and the Heisenberg model either. So this is not a complete theory, but to me, this suggests that the correspondence is not necessary only about the infinite temperature case. All right. Then the question, KPZ のサブクラスとして3種類の初期条件に対応する分布が紹介されてましたが、一般に様々な初期条件を選んだ場合も、この3種類の分布になるのでしょうか。それともこの3種類の初期条件の場合は、興味深い分布が出てくるから、これらのサブクラスが注目されているということでしょうか。Okay, the question is, so I explained 3 KPZ subclasses corresponding to the 3 kinds of the initial condition. The question is, what happens if we start from a general initial condition? Is it, does the distribution from a general initial condition fall into one of the 3 distributions I mentioned? Or it is just that the 3 cases can be solved exactly and show interesting results, and that's why the 3 cases are particularly focused on? That's a really great question. And this is actually answered in a slide that I skipped. What happens for general initial condition? Give me a couple minutes. Maybe no one believes. KPZ equation is mapped to the directed polymer partition function, this Z, okay? And then the circular case, to study the circular case, the initial condition we typically consider is this kind of wedge initial condition. I mean, we want to have a circular interface. So typically we consider this kind of wedge initial condition. In terms of Z, which is exponential of H, and if we take infinite slope limit of the wedge, actually the initial condition for the Z is a delta function. So, and then starting from this delta initial condition, mathematical physicists did derive the Tracy-Widom distribution, GUE Tracy-Widom distribution. Okay, so this is the solution for the circular case. Now, for general initial conditions, again, let me repeat. If we start from the delta initial condition, we get Z for the circular case. That is the GUE Tracy-Widom distribution. However, this is the green function, yeah? This is the solution. Circular case is a solution to the delta initial condition, delta function perturbation. For general case, for general initial conditions, okay, probably that graphic explanation is better. Graphically, we have polymer, directed polymer, and the lower endpoint is fixed at the origin. And that is fixed to the origin because of the delta initial condition. This partition function Z is physically, it is the statistical weight of the polymer distribution. It is delta at time 0. It means that the polymers, the polymer's location at time 0 is fixed at x equals 0. This is the meaning of this delta function. However, for flat case, Z is constant at the time 0, and it means that the polymer is uniformly distributed at time 0. So initial condition is different for the flat case, and that makes the difference between the GUE and GUE Tracy-Widom distribution in the KPZ equation. Now, for general initial condition, for general Z, we can use the result of the circular case as the green function. The solution to the general initial condition is given by this, by using this solution to the circular case as the green function. And in terms of H, it can be rewritten to this SQP problem. We have initial condition of H here, And we have the solution to the circular interface here. And we take the SQP over y. And more mathematically accurate expression is given in the literature in terms of the spatial process describing the circular case. And this is called the variational formula. And there is a very intuitive way to understand this. It is actually the Huygens principle of optics. Suppose your initial condition is like this. Then let us consider that this initial condition is a collection of point sources, and each point source produces a circular interface like this. Then this variational formula means that if we take the envelope of those circular interfaces, then we get the solution corresponding to this general initial condition. And then, of course, it depends on the initial condition whether we can solve this problem or not. But what we can show is the following. If we start from a curved initial condition, almost flat but slightly curved, then what happens is that the distribution is first like the distribution for the flat case. It is a GOE trace-evident distribution. And that's natural because the interface is only slightly curved. It is locally almost flat. We get the flat subclass. But as the interface grows, and then eventually the interface becomes sufficiently circular, and the distribution crossovers from the GOE trace-evident to the GUE trace-evident. So from such an initial condition, I mean curved initial condition, it is somewhere intermediate between the flat and circular subclasses, and what we have is the crossover from one to the other. We can also consider a Brownian initial condition. 全然2分じゃないな。I showed that the initial condition for the 1D KPZ class is the Brownian motion, but in order to be the stationary solution, the coefficient here must be precisely tuned. It must be d over 2 nu using the parameters of the KPZ equation. If the value of A was wrong, then it is not a stationary solution. In that case, there is a result that the distribution is not bike length, not trace-evident, so it doesn't fall into any of the 3 subclasses. It is something different. So the answer to your questions is that those subclasses, 3 subclasses, are not the only cases. There are exceptions, like the Brownian motion with a long parameter A. But they do represent the most 3 important cases. And for a simple, relatively simple initial condition, like a curved initial condition, we see crossover between one subclass to the other. So those are not the only ones, but they are, I would say, the most important ones. And they are solved exactly. Yeah, so that's the answer. Yes. はい、はい、どういたしまして。Are there more questions? I don't know to what extent I can extend. But since there's no more question up to now, and since we still have time in the get-together event, probably it's a good moment to stop.
Yes, maybe we can move on to obvious space.
Yeah. Okay, so thank you very much for everyone. And I'm very happy that many questions were asked. And I'm sorry again for the long lecture. Okay, so let me stop the screen sharing.